Welcome to the lecture series on reinforcement learning. In this video, we look at novelty and surprise in reinforcement learning. I would like to ask 5 questions. What is novelty and what is surprise? But then what's the difference between novelty and surprise? Why should novelty be useful? Why should surprise be useful? And moreover, why should we talk about all this in a reinforcement learning class? Let me start by showing you a set of images. Okay, that was the set of images. When I show it in a lecture, then I usually ask, where did you feel somehow strange, somehow surprised at some point in this series of images? And then people say yes. And then I ask, was it at the first image, second image, third image from the beginning? Or was it something like the third or fourth image counting from the end? And then people say, well, it was not at the beginning. It was towards the end. But that's a bit strange because the third image was absolutely novel. You had not seen it before. Yet you did not say it was surprising. The one image towards the end, that was novel, but this one you also saw as surprise. So novelty is not surprise. And what's the difference? I would like to make this point in the following. Surprise is against the model, is against beliefs, is against expectations that you build while you watch this sequence of images. So our first answer to question 3 is, what's the difference between novelty and surprise? Well, they're actually not the same. And the more precise answer is, surprise is against beliefs or against expectations, whereas novelty is not. Novelty is just, this is new to me, this is not familiar to me, I have seen it never before, or I've not seen it for a very long time. Surprise is different. Surprise violates expectations. So surprise is against expectations. And an example could be jokes. You build up expectations while you tell a joke, and then the punchline is, well, your expectations have go in the wrong direction, you are misled, and this is why jokes work. Now let's formalize this. In this first part, I would like to discuss with you a definition of novelty and a definition of surprise in a tabular environment. That means discrete states, discrete actions. So my events for the moment are states. One state is, for example, one image. The first time you see the image, it's new. When you see it for the fourth time, it's no longer new. There's a certain number of different images or different states, which I denote by these vertical lines, absolute value of this S. Now to calculate something like novelty, we proceed as follows. We count the events of type S up to time t. And this is my counter, which has a certain value, Ct, for my event type S, my state S, or my image S. I've seen this image 3 times up to now. And now the basic idea is that a higher count gives lower novelty. Now, there's also this notion of time spent in the environment. So we can bring up an empirical observation frequency and define it as follows. We take this count, we add 1, we divide by this number of time, the number of time steps in the current environment, and we also divide by the total number of states that exist in this environment. So now if you evaluate this for t equals 0, then you find the probability or the empirical observation frequency for all states is the same. It's just 1 over this absolute value of s, 1 over the number of states. And then to get to the novelty, we say the novelty of a state at time t is minus the logarithm of this empirical observation frequency Pn of s. That's novelty. Now what is surprise? Surprise has different event types. An event is the transition from a state, maybe in the presence of an action, to a next state. In the example of the pure image sequences that you watched passively, there's no actions, but there are still transitions S to S prime. So in a more general case, relevant for reinforcement learning, given action A in state S, will we end up in state S prime? And so surprise now proceeds as follows. We count the number of events of type from S with A to S prime up to time t, and this gives a counter for this transition, and then a higher count gives a lower surprise. The agent has spent the time t in the environment as before, and as before we now can define an empirical observation frequency, and this is the count for this transition plus 1, and then I have this C tilde, and the C tilde is the CT of SA to S prime sum over all different states S prime. And now this is my observation frequency. The definition of the surprise for transition given state S, given action A to state S prime is some prior probability that we compare with our empirical observation of this transition frequency. And so if I've seen a certain transition given ST, AT many times, then I will have a high empirical frequency, so I start to expect this. But then if this expectation is high compared to the prior, then the surprise is low. So the higher count gives a lower surprise, as it should be. Now the other case could be that it is in fact very low, but this transition is very low, but I have to compare it with a prior. And I will explain this prior belief or this prior for this transition probability a bit later. So here we compare two probabilities, a prior with my current belief for this transition, and this is called the Bayes factor surprise. Let's summarize. What is novelty? The novelty of a state is minus the logarithm of the empirical observation frequency. The definition of the surprise of a transition is also dependent on the empirical observation frequency. It decreases with that observation frequency, but we have to compare it with a prior. And this specific definition of surprise is called the Bayes factor surprise, but in fact there are at least 17 different definitions of surprise. But this is the one we will look at in the following.